Hello and welcome. I'd like to give a basic introduction to computational chemistry. So, basic idea of quantum chemistry is we're going to attempt to solve the Schrödinger equation. Luckily, we're going to attempt to solve this equation using computer software, so we're not going to directly try to solve any crazy or challenging equations by hand, but we have Hamiltonian operator operates on a wave function, returns the energy of the wave function. And to get a sense of some of the terms that are involved, behind the scenes in this calculation, we have the Hamiltonian broken apart into the kinetic and potential energy terms. And um, so we have our kinetic energy, 1/2 mv squared, for the particle being able to move. This is just a molecule of hydrogen. Of course, a molecule of hydrogen has some internuclear separation. It has the electron nuclear attractions of the two nuclei. The two electrons themselves are repelling each other. The two nuclei actually repel each other. And so and of course the electrons are attracted to the nuclei they happen to be closest to. And most of these terms are relatively easy to solve with equations, or easy-ish to solve with equations, except for the electron-electron repulsion term. You might imagine that the two particles that behave quantum mechanically are going to be the most challenging to treat. And this particular term here is one that leads to a variety of shortcuts that have been devised to try to approximate this term here. Some of those approximations, almost the simplest approximation you can make is treating each electron with the average field created by the other electrons. That's a basic description of what's called Hartree-Fock theory. This is really kind of our base method for doing a QM calculation would be HF theory. If we want to try to make an improvement using a more mathematical approach, if you treat error as a power expansion and try to carry out various degrees of expansion to try to improve upon the error that HF theory makes, then that's the basic description of what you might call perturbation theory. Molar placid is just one type of perturbation theory. It's relatively popular. MPX carries out the power expansion to the xth degree. MP0 would just be HF. That would just be the simple HF solution. MP2 would be the second order molar placid perturbation theory. This is a pretty widely used method, relatively fast. You can use this method on most of your organic size molecules. So think about molecules that have anywhere from, say, 1 to maybe like 20 heavy atoms. Heavy atom is anything usually other than hydrogen. So you can use this method relatively efficiently on most molecules you might be interested in from an organic perspective. Density functional theory computes molecular properties as a function of electron density. It's the exact DFT method has not actually been discovered. Modern DFT methods are parameterized with experimental data. So you use electron densities as your physically observable data that you can then program your DFT methods to then be able to work with a wide variety of molecules from just a small input set. Results are generally pretty good here. DFT methods can be characterized as hybrid or pure. Hybrid includes some of the HF exchange. Pure methods do not include the HF exchange. An example of a hybrid method that's relatively popular is B3-LIP. An example of a pure method that's relatively popular might be the MPW1, PW91. And a real basic introduction to DFT would be that you have an exchange term that comes first. B3 is the exchange function, and LYP would be the correlation function. Exchange deals with the exchange of electrons. Correlation deals with their electron correlation. And so then, like, the MPW1 is the exchange, and the PW91 would be the correlational. And then one other thing to mention is that most of these letters stand for people's names or iterations. So, like, B3 stands for Becky's three-parameter exchange functional, and LYP stands for Li, Yang, and Par. PW is Purdue Wang, and some of the ones might be iteration. Sometimes it's a year. Like the PW91 is the 1991 publishing of this method from these particular individuals. And then DFT method generally are pretty fast. I mean, they're usually faster than MP2, sometimes better. Sometimes the results can be inconsistent. What you're going to find with computational chemistry is that you're always going to have to find a way to benchmark. You're going to have to think every step of the way, what calculations can we do on similar systems that might be experimentally known, so you get a good comparison. And then usually you want to do something novel. You want to do something you can't do experimentally. So you might then say, okay, if we can have a data set that we have some confidence that this works, and have a different data set similar enough but maybe not known, we can then extend our likeliness that the methods are working and do good comparisons. Usually you might do more than one method is a good idea. If you can have multiple methods that have different types of approximations built into them and see that they work similarly, that would be good towards trying to prove whatever or support whatever you're trying to support. So a few things being shown here. We have a self-consistent field calculation. One thing I wanted to mention is that usually you have to sort of choose a geometry, choose a theory, choose a basis set, and then you kind of go off and hit go on your computer program. What the computer program is going to then do is guess the molecular orbital coefficients, set up a secular equation to try to compute the actual coefficients, and then iteratively solve and try to improve those coefficients until they have been solved for. So imagine you have a problem or situation where you have 40 equations, 40 unknowns. Usually when you have two equations, two unknowns, you just go through an analytical solution and you figure out your two unknowns. If you had like 40 equations, 40 unknowns, you probably just do come up with some iteration. You guess on them, see how good your guess was, and kind of keep trying to improve upon your guesses. And then, so there's some algorithm that you have to, or some convergence criteria you have to satisfy for the MO coefficients to become optimized. But we haven't even like touched the geometry yet. So the calculation would first take your input geometry, solve for the MO coefficients, use those MO coefficients to determine the energy of that structure, and then it would try to perturb the structure, try to follow the force gradients to minimize the energy of the molecule, adjust the bond lengths, angles accordingly, come up with a new geometry, and go through an MO coefficient guessing and solving through an SCF cycle or self-consistent field cycle approach. And then you keep iterating the geometry until you satisfy your convergence criteria. And then you might do other calculations. One of the most commonly done calculations after you do a geometry optimization would be something like a vibrational frequency calculation. So you can understand the IR spectra of the molecule. This also gets you some thermodynamic parameters so you can compare like the enthalpies, the Gibbs energy of the molecules at some given temperature, usually room temperature. So on the left here, you see a diagram kind of showing you a local versus global minima. I like to think of a molecule here. Think of something like ethylene glycol. So you have CH2CH2, an ethane ring with a hydroxyl group on the 1 and 2 carbons. So that's ethylene glycol. So imagine, where do those two hydroxyl groups want to point? Are they going to be anti-relative to each other, opposite? Are they going to be staggered? Are they going to be eclipsing? You can imagine there might be different local minima, there might be maximum points. Whenever you feed in a geometry, usually you're just going to find whatever geometry, whatever minima happens to be closest to your starting point. So if we start with ethylene glycol with the two hydroxyl groups eclipsing each other, we're probably going to find that local minimum, or whether that happens to be a maximum point, we're going to find that particular point on our potential energy surface once we go through our geometry optimization calculation. You may wonder, is that the global minimum? Well, for most molecules, if you really want to know you have the global minima, you're going to have to sit down with a pen and paper or have a good model in mind of what the molecule looks like. And from there, you can sort of build each of your different local minima and then optimize each one of them separately and then compare their relative energies. And you're, of course, going to determine the global minima to be the one that's lowest overall in energy. So whenever we have this local minimum problem, what this sort of means to us in the computational world is we have to find some way to consider all the possible minima, evaluate them, identify which one's lowest in energy. Now, if you want to extend this approach into bigger molecules, maybe biomacromolecules, this becomes really hard to do with pen and paper. You're not going to do it that way. You're going to come up with a way to do like a molecular mechanics type of dynamics simulation. So you're going to use dynamics to try to simulate where that global minima happens to be and go about the problem in a whole different way. For relatively small organic molecules like we're going to work with in this class, it's really easy just to come up with, okay, there's 3 different minima. Let's evaluate the 3, compare their energies, and move on. I think that's something we focus a little bit more on when we get to experiment 6 down the road. Something I wanted to mention, if you're really excited about computational chemistry, you want to find out more of what goes on behind the scenes in the calculation than what I'm talking about here. There's 2 courses that we offer at OSU for undergraduates. I believe Dr. Spinney teaches both of those. One is on computational chemistry, the other is on computational biochemistry. I don't think one is a prereq for the other, so you can take either one or both or neither, whatever fits into your desires. I just wanted to make sure I mentioned that those courses exist if you're interested more into learning more what goes on behind the scenes in these calculations. What I'm showing here is a slight difference of the SCF cycles for an HF versus a DFT calculation, where you're guessing a density matrix, solving the Kohn-Sham density matrix, but in a similar type process for your DFT calculation compared to your Hartree-Fock-based method type calculations. Okay, so there's some other methods. CI, what this allows us to do, it's kind of hard to picture, but if you imagine having an MO diagram where you have some occupied molecular orbitals and some unoccupied molecular orbitals, we might call those virtual orbitals in the computational world. But you have your filled orbitals, your virtual orbitals. What you can then do is allow the electrons to excite or move into some of those virtual orbitals. And what that's allowing the electrons to do is to sample more of space, to spread out. Of course, electrons repel. They may be happier to some extent being in different orbitals. What this allows is for the energies of all the orbitals are being considered to really be more accurately modeled. And so what this allows is the molecule to do what it can really do in reality, which is move its electrons around throughout the molecule and sample space surrounding it. And so CI allows you to do some of these electron-electron interactions. So you have CIS, does single excitations. It moves like one electron around at a time through the molecule or through the virtual orbitals. This is useful. This is what's done if you do a UV-Vis spectra calculation. And I'm actually trying to think if we actually do any of those this semester. I don't think we require you to do those, but some of you may want to look into some of those for your projects down the road for the research project. CISD does a single and double excitation, so it can move two electrons around. At a time, CISDT does singles and doubles, and within those, some of the three electrons moving around. And then QCISD is a quadratic CI method. And these are all generally pretty intense methods. They take a lot of time. These are only going to be doable if you have relatively large amounts of computational expense or really small molecules. So you're talking 1, 2, maybe 3 heavy atoms for these types of calculations to finish with reasonable size basis sets in a couple of hours. Luckily, we're going to be doing most of our calculations this semester with a supercomputer center, so we can do a lot of these. Unfortunately, we only get like 1 or 2 hours maximum per calculation before we have to restart a calculation. So we have to try to keep our calculations relatively quick. CC is another method, couple cluster, does a sum of clusters of excitations. It's kind of like the CI method, but has more of a algorithm to choose only certain types of excitations. Results are pretty good. CI/CC methods, pretty highly regarded. These are often called post-Hartree-Fock method. Post-Hartree-Fock methods. Computational time here would be HF, generally going to be your fastest. MP2, B3 lip, about the same amount of time. I think B3 lip, once you start getting into larger molecules, starts to get a little bit faster. Another way of putting that is MP2 tends to scale a little bit poorer, meaning as molecules grow larger, MP2 is going to take a little bit longer, B3 lip, not as long. MP4, CCSDT, CI fold, these methods are going to take a lot more time, especially as molecules grow. The issue here is scaling. If you look at HF and B3 lip, they're scaling at about probably end of the 3 or end of the 4. What that would mean is if you take a calculation, let's say we do a calculation that takes 10 minutes on some size molecule. If we double the size of the molecule and the method scales at end of the 4, then doubling the calculation is going to take 2 times 2 times 2 times 2. So 2 times 2 is 4, 8, 16 times longer. So at end of the 4 scaling, 16 times longer. So if you have a calculation on, say, a molecule takes 10 minutes, the dimer of that molecule would take 160 minutes. That's a lot longer. MP2 maybe scales about end of the 5. So it's going to take 32 times longer. So as MP2 calculations, as you grow bigger and bigger, are going to take longer and longer. MP4, CCSDT, even worse, end of the 7, CI full, MP7, 7th order molar cluster perturbation theory, end of the 10. 2 to the 10, I think is 1024. Let me pull out my calculator here. Well, let's just say it's a big number. So it's going to be a big number. I think it's 1024 is what 2 to the 10 is. So you do a calculation on one molecule, it takes 10 minutes. The dimer, 1,000 minutes. Or not even 1,000 minutes, 10,000 minutes. It would be 10 minutes for the first calculation times 1,000. So 10,000 minutes for the dimer if you're using an FP7 method. One of the things that you'll get in the hang of here is if you start your calculations relatively small at the lower end of your methods. So start with HF. We'll talk about something called a basis set. Start with a relatively low method, small basis set, get a sense of how long that calculation takes. If it takes like 2 seconds, you can probably move into B3 bigger basis set. If that's fast, you can probably then start thinking, okay, yeah, I can probably do some of these CISD methods, CCSDT methods, and have those calculations finish in a relatively reasonable amount of time. Calculation types we do in 4410, we can do energy calculations. Day 3 of our activity, we'll be doing some calculations on methane, where we're going to be trying to remove an electron. We'll do that just by changing the charge to plus. So we'll look at methane with a positive charge, lost an electron. We'll compare some calculations where we don't allow the geometry to change. So in that case, that's an energy calculation. If you start with the structure of a molecule and you don't want that geometry to change, then we want to choose an energy or a single point calculation. Equilibrium geometry or an optimization, an opt, and Gaussian. See, we use both Spartan in person, and then we'll use Gaussian to run as our engine with WebMO. Our equilibrium geometry, these are optimizations. So these are just optimizing the geometry. Our vibrational frequency calculation is a freak calculation. Oftentimes in Gaussian, it'll be called an opt plus freak. It's an IR spectrum calculation if we're doing this in Spartan. I don't think we're going to do much Spartan this semester. Usually we do that in person. I don't think we're going to be too in person with our computational work this semester. Probably a lot of this being done from home using WebMO. WebMO will have its own video, so check those out as we get into those labs. But vibrational frequency analysis, this allows us to establish if our structure is a minimum energy structure or a transition state. A minimum energy structure will have all real vibrational frequencies. A transition state will have one imaginary vibrational frequency, all the others being real. So if you're imagining a transition state being like the maximum point loses one of its real vibrational modes, replaces it with an imaginary mode. The way this mathematically works out, you end up with a negative a negative force constant you're trying to take the square root of. You're trying to take the square root of a negative force constant. That's where you end up with these imaginary vibrational frequencies. Okay, and so then sometimes you end up with a structure that might have two imaginary frequencies. Sometimes they look negative, but really they're imaginary. But if you see a negative or imaginary vibrational frequency, there's actually two of them. That's what you call a higher order saddle point, which has no physical meaning. So we want to ignore those as being minimum energy points should we find them. But we also get thermodynamic corrections. And this is something we'll look at in the activity 1 with experiment 5, is looking at these different thermodynamic corrections and how they're made from the minimum energy structure's energy. So when we do an energy calculation, we'll get the energy of a molecule, usually in like Hartrees per one single particle. So all of our calculations that we're looking at this semester assume you just have one particle isolated in the gas phase. And then you can apply some thermodynamic corrections so that you can get the like enthalpy and the Gibbs energy of that molecule, but still as a gas phase particle, not as whatever the substance may exist as. So say you do water, a calculation on water. It's still a gaseous particle, 0 Kelvin in the energy calculation. And then if you do a vibrational frequency analysis, you can then get your thermodynamic corrections up to 298 K, but still for a water gas phase particle. And so then we'll talk about how the thermodynamic parameters connect to the results that you can get. And then we can also do profile scans, a potential energy surface scan. We'll do some of these actually in experiment 4. We'll take a look at some of these where you actually do a bond length scan on something like HCl. So you have HCl compressed, allow that bond length to change, and each step of the way calculate the energy. You can also do potential energy surface scans to vary bond length. You can vary bond angle or bond dihedral. A bond dihedral is, well, I don't know, without an ability to look at dihedral, probably doesn't make sense to define what a torsion angle is, but you can do those as well. And we can talk about those later if we need to. As this connects to experiment 4, where you'll talk about the harmonic oscillator approximation and how this relates to the stretching frequencies of real molecules. A real molecule is best described as a Morse potential. The Morse potential describing the energy plateauing as a bond is stretched. harmonic oscillator just assumes you have a string, or excuse me, a spring connecting the two masses. Okay, so the idea is bond length, or excuse me, if you do a energy calculation, through the optimization calculation, you get the energy of the molecule at the bottom of this potential well is all you know. You do the vibrational frequency analysis, you determine the fundamental vibrational frequency, and then half of that vibrational frequency is the energy it takes to get up to V equals 0. So the sum of 1/2 h nu for all the vibrational modes of the molecule is the 0 point energy. And so the 0 point energy is the energy it takes to get up to V equals 0. And then you have the heat capacity and the entropy terms, which we don't get into too much of a description of how they're calculated, but those are computed as well. And those allow you to obtain the enthalpy of the molecule at 298 K, and it gives energy at 298 K. So a quick description of basis sets are that what we need to do is take our hydrogen-like functional forms, e to the minus r functions, and turn them into Gaussian functions, e to the minus r squared terms, simply for computational time. The computational calculations that need to be done are a lot faster on Gaussian type functions as opposed to hydrogen-like functions. Now, if you look at the functional form in the solid curve here, you see that the dash curve Gaussian form functions don't quite add up. They don't exactly mimic the equations we're trying to model. So we take a series. We take a series of Gaussian functions and use those to try to replicate our hydrogen-like functions. So now as you see a basis set go from 321G to 631G, you're having more Gaussian functions. More Gaussian functions is a bigger basis set. It's going to usually give you better results. If you see more digits, that gives you an extra what's called split to your basis set. So you can have functional forms that are maybe a little bit further away from the nucleus instead of closer to the nucleus. So you can sort of have different functional forms at different radial lengths compared to the nucleus. Just know that as you're adding symbols and numbers, and as those values are going up, you're going to a bigger basis set. We're going to talk a little bit more about the specific sizes of different types of basis sets later into the experiment. This is just showing polarization functions with a star symbol or with a D term. Polarize your orbitals, which is good, gives them more functional form. Diffuse functions adds bigger functions to heavy atoms. We can also add P functions. We can like polarize our H atoms with P functions. And so that takes your like 1s orbital and polarizes it with a P function. The key takeaway here is a 631G star would be a bigger basis set than a 631G. So as you start seeing Ds or DPs, that those symbols are showing are going to larger and more flexible basis sets. And then diffuse functions, the plus symbol, 2 pluses adds that diffuse function to heavy atoms as well as light atoms, but those are even bigger basis sets as well. So to count up how many functions a particular basis set gives to a particular molecule is a type of calculation we'll look at towards either the end of day 1 or day 2. I can't remember what day it is on experiment 5, but we'll take a look at that in a separate video in a little bit more detail. Some methods do what's called a basis set extrapolation. I just wanted to mention this here, that you can imagine doing a calculation with a small basis set, bigger basis set, even bigger, and kind of looking for your basis set extrapolation. And there are methods that will actually do a basis set extrapolation within one single calculation that you submit. So there's different methods that can actually do a basis set extrapolation within the calculation that you might submit just one time. Now, you can imagine those usually take a fair amount of time. Okay, so I think that's the end of the video here. So one of the keys is that whenever you're doing and running a computational chemistry calculation, some of the important things are you have to build a structure. You have to kind of know what it's supposed to look like so you can have some sense of what the molecule is supposed to look like. You then have to choose a type of calculation that you're going to run. You have to choose the method, like HF, MP2, B3-LIP. So you have to choose the method that you're using, and then also choose the basis set. The basis sets are going to look like something, something, something G usually, so like 321G, 631G star, things like that. We'll also talk a little bit next time, or in a specific video on basis sets, about a different type of basis set that have like a CCPVDZ or CCPVTZ type nomenclature system. We'll look at those basis sets as well. So you'll specify a method and a basis set. type of calculation, hit submit, analyze the results at the end of it. One of the most important things to remember with computational chemistry is you almost always get a result. So what you have to know how to do once a calculation finishes is how to analyze the results so you know what you're looking at. So just know um, calculations may or may not be what you expected them to be. You have to know how to analyze the results. You also have to know how to set up and run the calculation you intend to run as well. So use the WebMO videos as well as this video, as well as some additional videos we'll put up to help you understand what goes on in these calculations and then analyze the results. All right, thanks for the attention.